Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these Tech Talks have been designed to provide straightforward insights into radio frequency components, the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yes, thank you, Paul. So today what I'd like to talk about really are what is a hybrid, a little bit about theory, and really also how they work, and then move into applications, and then sum up with some of TRM's differentiators.
Well, that sounds good. And maybe you could start by giving us a more technical definition of a hybrid as opposed to my layman's version.
Yeah, very good. Hybrids are really an interesting thing, and I think the word can be a little misleading. A hybrid, the dictionary definition of a hybrid is a device that combines 2 or more different technologies or functions into a single unit. The classic example of what we talk about these days are cars, where we go in there and we combine a gas engine and an electric engine. Hybrid circuits in electronics also typically involve, again, combining technologies where we have lumped elements and open die sort of components into a single package. Though neither of those detailed definitions are what a passive hybrid does.
Well, maybe you could tell us a little bit more then about how they fit into RF applications.
Sure. So the word hybrid that we use that applies to RF applications really goes back to the phone company. So this goes back literally to the 1800s when the phone was first developed. And what they had then was they had a multiple wire system. So you can have a receiver and a microphone, or a speaker and a microphone, so you can talk across the wire. The very, very early phone systems used 4 wires for this: 2 wires for the speaker and 2 wires for the microphone. Very early on, they came up with a circuit that took those 4 wires and combined it onto a 2-wire network. This actually made stringing the wires have this system have twice the capacity. So this was a major breakthrough for the phone industry. And basically, the hybrids, the microwave hybrids that we build here today, are based on a lot of the same math and the same ideas that are involved in that initial telephone network.
So what parts of the phone, maybe you could give us a little more details on that.
Sure. So these are 2 sketches that I was able to pull off the internet of the circuit that is actually in the handset of the telephone. And you see on both of these circuit diagrams on the left-hand side, those are the 2 wires that go out to the street, out for the line. And then you will see there that there are 2 areas, one where the receiver is put on there, and that is obviously where the speaker is for the headset, and the signal in is the microphone input. So what this allows you to do is it allows to have a common transmission line for both a send and receive signal. By the way that these hybrids are wound, the signal from the microphone and the signal from the speaker are 180 degrees out of phase from each other. And then on the opposite end, they are, again, 180 degrees out of phase from each other, so that the microphone of one system talks to the speaker of the other system. What you see here basically are 2 different realizations of that same network.
Okay. And are the hybrids, were they also used inside the telephone itself too?
Yeah, so they were also used on the transmission lines. Now, got to remember, if you have a microphone, the signal levels are very small, and it's not going to travel for hundreds of miles. So they have to every so often they have to amplify the signal. Well, how do you do that in both directions? Well, you take another version of that same circuit, and you can then again split out the signal and put amplifiers. Uh, uh, one amplifying in one direction, the other amplifying in the other direction, to be able to go ahead and increase the range of the telephone. Again, this hybrid network is very, very similar to the 0180 hybrid that we build today for microwave devices.
Okay. Now, is it also true that a hybrid can be part of a network?
Sure. Now, what we do is when we build these hybrids, what they are these individual building blocks, very similar to what was in the phone system, and we connect these up, and we create these phase combination and dividing networks, so that we can go ahead and have these higher order functions. By definition, RF hybrids have 2 inputs and 2 outputs, or they're 2x2 networks. Hybrid networks can divide or combine signals, either forward or reverse. And there are 2 major classes of these hybrids. There's the 0180 hybrid, which is a direct descendant of the phone network, or the 90-degree hybrid, which is related but a little bit different.
Okay. Now, I've heard you refer to the networks as being directional. What is that about?
Well, again, based on the example of the telephone, by being directional, it means that the energy only flows in one direction. And what that does for you, for example, in the hybrid network on the phone, is that it allows you to be able to go in there, speak into a microphone, and not have it repeat right back out the speaker, and we get this echo or feedback going on. What that does for an RF network is it allows you to take various signals and have them be isolated from each other, so that when you do your combining or dividing, there isn't crosstalk going on. So they're very useful in those for those applications.
Okay. Now, what's the main difference between a 0 to 180-degree hybrid and a 90-degree hybrid?
Yes, the big difference there really has to do with the phase relationship between them. The 0180 hybrid has 2 inputs and 2 outputs. They're also isolated from each other. There's an equal power split between from any one of the inputs to both outputs, and that the nature of this hybrid, if you have the 2 outputs and you use it as a divider, the sum output obviously has the 2 outputs in phase with each other, and the delta input has the 2 phases out of phase with each other. The 90-degree hybrid has a 90-degree phase relationship, as opposed to being in phase or directly out of phase.
Okay. Maybe you could tell us a little bit more on that end.
All right, so this over here now is getting into what TRM does. The lumped element 0180 hybrid, again, and it's not really quite obvious to see unless you're an engineer here, but the transformer network here can be directly derived from the telephone circuit that we talked about earlier. This is and this network over here builds up what we call the lumped element 0180 hybrids. The schematic, as well as the assembly drawing there, does show one of TRM's very low power 0180 hybrids. These are direct descendants from the telephone hybrid. They work very well, extremely broad bandwidths, up to 100-to-1 bandwidths, bandwidths of say 5 megahertz to 500 megahertz. And these work very effectively up to about a gigahertz or 1,000 megahertz with this sort of technology. There are some other things we can do there to drive that frequency up a little bit. The circuit does change a little bit as far as how the actual layout goes. This also works very well for very low frequencies. We can go with some fairly high permeability ferrite, for example, to drive this down to very low frequencies in the kilohertz range if we have to. So there's a very versatile sort of circuit.
Okay, that sounds good. Could you tell us a little bit about ring hybrids?
Sure. Now, ring hybrid is a now we are moving away from the lumped element telephone kind of network into other ways of getting a 0-180 phase relationship. Um, these again have the ability to generate either a sum delta output um, into two outputs, very similar to the way that the previous one did. The big difference here is that this over here can now work up at very high microwave frequencies. This sort of circuit here can be used right through, 20, 30, 40 gigahertz if need be. Um, uh, this over here does have the drawback of being narrowband. It has about a 20% bandwidth. It can now be printed technology, so we're talking about microstrip, strip line sorts of technologies. Coax can also be used to build this. And the interesting thing about the coax is if you build it with coax, you can increase the bandwidth of this because you can use the coax as a reversing line, replace the 3/4 wavelength long delay line with a 1/4 wavelength line, wire it a little bit differently, and increase the bandwidth of this device up to about an octave. And TRM does do that for some of our ring hybrids, depending on the frequency and power requirements.
Okay, now I've also heard you refer to a tapered line. Can you explain that a little bit, please?
Sure. And again, there's different ways of generating this 0-180 phase relationship. The example on the screen here is a very broadband tapered line. And as you can see on the circuit, this is a tandem configuration. There are two couplers that are connected heel to toe. Each of these tapered lines has a 9-degree phase differential off of them. And when you cook them this way, you do generate the same sum delta configuration. One of these inputs will generate in phase outputs to the two outputs, and the other input will generate a 180-degree phase offset between the two outputs. Again, amplitude balance is maintained for either input, and this part is fully symmetrical, whereas if you were to combine parts, you would also get the same sum output and delta output.
Okay,
Again,
thanks. I'm sorry, go ahead.
I was going to say also, this sort of construction is used, again, ultra broadband, 15-to-1 bandwidths, 20-to-1 bandwidths, but it's also used at very, very higher microwave frequencies. These are typically not used below about a gigahertz, only because of the physical length of the line. Tapered lines tend to be very, 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 you need to have them on the order of 3/4 or half a wavelength long in order to be able to get the high pass function to operate. So therefore, the frequency of operation for these things tends to start at about a gigahertz and up.
Okay, I had a note here also to ask you about pseudo hybrids. How do those differ?
Pseudo hybrids are yet another variation of this thought. With this particular example over here is that there is a 90-degree hybrid, which is shown on the bottom of the sketch over here. It's a straight 90-degree 1/4 wavelength coupled line. This could also be done with a stepped tapered line as well. This generates a 9-degree phase offset. In the middle of this diagram over here, what you will see a shift in phase shifter. That's the coupled line in the middle that kind of feeds back on itself. That over there generates a 90-degree phase offset. As a result of the 90-degree phase offset of the coupler being added in series with a 9-degree phase shift element, this also generates a 0-180 hybrid when driven from the sum delta ports. So driving this in the forward direction, it looks identical to the tapered line coupler that we just discussed. The reverse of this, though, is that when you drive this backwards, the phase relationship between the sum and the delta port is not 180 degrees like it is in the previous configuration. That phase is 90 degrees. This can have an effect if you're using this in beamforming applications. We have to be very cognizant of the fact that the phase shift is not fully reciprocal. Now, there are times when having a non-reciprocal phase relationship is advantageous to the particular network that you're putting together. And it's very important to understand that this class of hybrids is not fully symmetrical. TRM builds a lot of hybrids this way. A lot of our octave bandwidth 0 and 80 hybrids at higher strip line frequencies from 250 megahertz up through 20 gigahertz tend to be this configuration. Because this is a single quarter wave coupled line, the physical size of this is much more compact than what you get with the tapered line configuration. So therefore, there's a lot of applications where you want a good 0 and 80 hybrid only working in one direction, with being a little tighter on space. Very often we will go with this sort of configuration.
Could you maybe give us just a little bit more detail about the phrase coupled line? You've used it a few times here.
Sure. So a coupled line leads us directly into the 90-degree hybrid. And what this is that if you have two lines, two transmission lines that are in very close proximity to each other, the electric field and magnetic field generated by current going down one of the lines induces a current in the other in the other line in the opposite direction. This is one way of generating a 3 dB power split is by taking half the energy from one line and having it couple over to the other transmission line. This is a little bit of a precursor to the directional coupler discussion that we're going to be having. But this over here happens for the special case of a 90-degree hybrid where half the power is coupled across those lines. For a quarter wavelength section, the phase shift across that coupled line is 90 degrees. So these sorts of configurations for the single quarter wave, like I'm showing in the diagram here, has about an octave bandwidth. What we can do is we can go with a symmetrical stepped taper, and this sort of configuration can be expanded at bandwidth up to about a 10-to-1 bandwidth when we add say 9 sections to it. What this does over here is this creates a 90-degree phase offset between the two outputs, between the one input. This can be a very effective way for generating networks that require a 90-degree phase shift. A lot of antenna networks, for example, require 90-degree phase shifts. We also can use this sort of configuration as power combiners. If we use a 90-degree hybrid to split the signal, put amplifiers in series with the two outputs, and then use the reciprocal 90-degree hybrid to recombine these networks, we can get very efficient power combining. And as you can see by the network, there is no resistive element in here, so therefore a lot of the thermal characteristics that are required for those combiners really gets mitigated by the fact that we don't have internal resistors to worry about power dissipation for. So this class of hybrid again works quite nicely if a 90-degree phase shift is required as opposed to a 180-degree phase shift.
Okay. You've also mentioned the term lumped element several times. Can you explain a little bit more about that?
Sure. And basically, you can build the same 90-degree hybrid in a lumped element. Again, going back to the technology of the telephone, we can have a transformer and capacitor network that can generate, instead of having to generate a 180-degree phase network, which is the 0 and 80 hybrid, which is based solely on transformers. If there are capacitors in that network, they're there more or less just to tune out any kind of unwanted stray reactances from the transformers. The 90-degree hybrid built in lumped elements, though, the capacitors work actively with the transformer to propagate the proper phase shift. And these networks over here typically operate over about an octave worth of bandwidth. So again, narrower bandwidth in the 0 and 80, which looks very similar from a technology standpoint. So these work over about an octave, and they work quite nicely. These are the sorts of configurations that we use when we go very low in frequency, something below a gigahertz again. And what we're looking for here is about an octave worth of bandwidth when we require a 90-degree phase shift.
Okay, that makes sense. Earlier we said that hybrids can sometimes be very good choices when people are faced with different types of engineering or maybe design restrictions. Maybe you could tell us a little bit more about some of those applications.
Sure. So hybrids are building blocks. They are used for building things like beamformers, monopulse networks, anything where you have to have a phase differential between two outputs, something other than 0 degrees, and which is where power dividers come in. And quite frankly, you can also use a hybrid as a power divider if you have a 0 and 80 hybrid, if you require a 180 phase shift. There are some topologies that are quite nice to be used, and sometimes in some applications it makes sense to use a hybrid in lieu of a power divider for certain applications. But basically, hybrids are used as building blocks, for beamformers, monopulse networks, Butler matrices, quadrature feed networks, circular polarization for antenna feeds, some difference networks. All of these higher order modules are nothing other than a combination of 2 or 3 or 4 or 8 of hybrids built in a single network, feeding off the other, and the net sum of all of these hybrids working together builds these sub networks.
So can hybrids also be used as power combiners?
Absolutely, and that is really where we want to go in there and kind of talk about it. I know I talked about that in the last talk that we did. Hybrids are tailor-made for power combining. The fact that Delta port is available to take any of the extraneous non-combined power and port it out to a high power 50 ohm termination, it is ideal as a power combiner. So it's a great application for a hybrid.
Okay, so maybe we could talk a little bit about TRM's role. I mean, we've said that hybrids are in many cases ideal choices when faced with different types of design restrictions or whatnot. What are some of the things maybe that the team has to do to make these innovative modifications?
Yeah, so what we do here is, as I sort of highlighted going through this here, is that there are lots of technologies that are available to be able to build a hybrid. TRM uses all technologies available: lumped element, strip line, microstrip, coax, and so on. And basically, we use every technology available with the exception of waveguide. So therefore, there are certain times for certain applications, whether it's a power level, whether it's a frequency range, where one approach will be better than the other. TRM uses all of these technologies. We're not necessarily going to be driven into the one technology that we do. So therefore, we can usually come up with a better than solution and use the best of all technologies.
Okay, and what about screening and packaging? Is that part of the mix?
That is absolutely part of the mix, Paul. So really what we do is, in addition to offering the best technologies available for any one particular design, we also we offer custom screening. We're happy to do that. We will also very happily package these parts to meet whatever requirements are needed, whether it is a special connector, whether it's a special mounting configuration, whether there's a special form factor. We're happy to work with the customers to go through there and develop the product that really solves their problem and satisfies their needs. Also, we go through there and we will combine products if necessary to really fully optimize and optimize both performance and size and weight for our customers.
Well, thank you, Shaun. I think that you've cleared up a lot of the questions associated with hybrids and their use and some of the different things that TRM's team needs to do to make them fit the customer applications. We're not going to have time for direct questions today, but if you are on the session and you're a customer, we are very happy to answer any questions that you might have. And before Shaun does a quick summary, we'll have Shaun do a quick summary, and then we'll show you our hotline number. And if you are one of our field reps, you know that you could go through the rep portal to pose questions or certainly work through your camp. So Shaun, maybe you'd like to summarize today's discussion.
Great. So hybrids are 4-port devices, which means there are 2 inputs and 2 outputs that can be used simultaneously to divide or combine signals. Depending on the exact configuration of these networks, we can either design to be in phase, out of phase, or quadrature phase, which is the 90-degree phase shift. They can be built using a variety of technologies, whether it's lumped element, printed circuits, microstrip, coax, and very often, I think to remember this, is that hybrids are the building blocks of beamforming, where you have inputs with controlled outputs at various phases, and also hybrids are fantastic blocks to be used for power combiners.
Excellent. Well, once again, thank you, everyone. You can see our engineering hotline number here on the screen, 888-677-6877. And in case it's helpful, our next tutorial next month will focus on couplers. Thank you so much. Thank you, Shaun.
Thank you.